Now we continue with Chapter 13 and our discussion of functional groups. We spent all our time in the first video going over general structural concerns and looking at alcohols. So that's a very important first group. Now we're going to jump into other groups, and our first ones that we'll look at are what are called thiols and ethers. So we'll start off with thiols. A thiol, sometimes we call this a mercaptan, so a thiol and a mercaptan those are synonymous. They contain an SH functional group, so it looks like an alcohol, but it's got sulfur there instead. So one of the big keys is thiols stink. They stink really badly. And it turns out there's a good reason for that. It turns out that the thiol group, a lot of these are very toxic systems. And a lot of this is based off of, your body's response is based off of hydrogen sulfide. So just like alcohols kind of parallel water because they have an OH group there and they have water solubility, thiols in some ways parallel hydrogen sulfide, that is H2S. And H2S is a highly toxic compound. It does occur in nature, but our bodies have kind of evolved to sense that extremely sensitively because it is so toxic to us. So thiols stink. Skunk smell is based on a thiol, and the smell you get from natural gas, that's actually something that's added so that you know that you've got gas in the air. Of course, propane has no smell. Methane has no smell. And so a natural gas leak, your body wouldn't sense it, and that could be extremely dangerous because it's combustible and explosive, actually. But to avoid this, we simply add very small traces of a thiol, which burns quite nicely. And it's not. It's added. It can be added in part per billion level, or very, very, very low levels. But our bodies are extremely sensitive to it. So if we're going to name a thiol, we simply name the thiol. We add our suffix thiol to the name for the alkane, just like we did with the alcohols. But now, rather than just calling it an ol, we call it a thiol. So CH3SH would be methane thiol, just like we had methanol. Now we've got methane thiol. Thiols undergo oxidation, and this turns out to be really important for our biological systems. So it turns out that a lot of our proteins in our body contain thiols, and those thiols undergo an oxidation reaction. Now, in contrast, we don't form something that looks like an aldehyde or ketone. We form a disulfide. So when you have a thiol, these oxidize to form a disulfide. And the disulfide has a sulfur-sulfur bond in the center. So this oxidation occurs fairly readily. You can use oxygen, iodine. Now, hydrogen peroxide is a pretty strong oxidizing agent, but even diluted in water, this works. And so you can see at the bottom here, as an example, we have ethane thiol. And if ethane thiol undergoes oxidation, it produces diethyl disulfide. The two hydrogen atoms leave. So that's the oxidation. When you lose hydrogen or gain oxygen, that's an oxidation process. So the two hydrogen atoms that go away, we get water produced and a disulfide is produced. Now, if you do a much stronger oxidizing agent, you again don't produce something that's analogous to an aldehyde. You produce a sulfonic acid. We can look at the structure for sulfonic acids and lecture if that's of interest to you. Now, just like we have an oxidation reaction, which is reversible, we can do a reduction reaction. So reduction is the reverse of oxidation. So just like before, when we took and we oxidized a process, we can do the reduction to go in the other direction. We can take a disulfide and we can reduce it effectively by adding hydrogen to produce a thiol. And here's an important example. This is a molecule called cysteine. And cysteine, if this undergoes reduction, produces cysteine. And a common reducing agent is dithiothreatol, which is important for biochemistry. Now, it turns out, this is just a side point, it turns out that curly hair versus straight hair is based on disulfide linkages. Proteins make up the bulk of our hair, and proteins have these disulfides in them, and the disulfides relative to the thiol ratio determines the curliness of the hair. As disulfides are formed, the proteins fold together and the hair becomes curly. If you take that disulfide and you reduce it back to the thiol, you open the protein structure back up and the hair is straightened. So when hair is chemically curled or straightened, that's due to the processes of oxidation and reduction, respectively. So that's thiols. Next up are ethers. Now, an ether is a structure that looks kind of like an alcohol, except the hydrogen is gone and been replaced by another alkyl group. So now you have an oxygen with two covalent bonds to two different carbon atoms. So the general structure then would be ROR, and the R's could be the same or different. If they're different, you might have R and R prime. You have two alkyl groups. It could be a methyl group, ethyl, propyl, and so forth. All right. Now it turns out that the oxygen, of course, has two lone pairs. And just thinking back to what the shape of this looks like, those two lone pairs coupled together with the two bonding pairs, we have 4 electron groups or 4 electron domains, and that's a tetrahedral structure, so that's tetrahedral electron groups. But since 2 of them are lone pairs, the molecule looks bent in that region. So in this figure here, you've got a very common ether that's used. It's something called diethyl ether. Okay, and diethyl ether used to be used quite a bit as an anesthetic. Now, the naming of ethers follows a very standard pattern. So the systematic name of an ether, we start off with the prefix for the shorter R group, followed by oxy, and then we end the alkane name with the longer R group. So for example, CH3OC2CH3 could be methoxyethane. Another way to do this is to name the parent chain with an OR substituent, methoxy, and so this is what's called an alkoxy group. If the longer R group has more than 2 carbons, we use kind of a different approach to doing this. So that's shown here. In A, we have 1-methoxypropane, and in B, we have 2-methoxypropane. So there's an older but still widely used name for ethers that follow the format of the alkyl ether, where the alkyl groups are listed alphabetically, followed by the word ether. So this is probably an extremely common name that you will see for a lot of small, important ethers. So if the dialkyl or the alkyl substituents are the same, then we would call it a dialkyl ether, and we'll see examples in just a moment. So if they're both methyl, that would be dimethyl ether. So here's 3 examples here. So these are 3 common named ethers, not using the methoxy approach. So in A, you have 2 methyl groups, so we call that dimethyl ether. In B, you've got a methyl group and an ethyl group attached to oxygen, so we call it ethyl-methyl ether, following the alphabetical ordering. And in the third one, then we have a propyl group, but we're bonding to the central carbon. So we could call that 2-propyl or isopropyl. And then we have a methyl group. So that's isopropyl methyl ether. So you should know both of these naming schemes. Ethers are used as anesthetics in surgeries, and diethyl ether used to be used. Modern approaches use halogenated ethers. So diethyl ether turns out to be actually pretty flammable, and so that produced a combustion hazard during surgeries. The halogenated ethers are better anesthetics, and they're not flammable. Just like we talked about, the halogenated hydrocarbons are used as CFCs because they're resistant to oxidation. The halogenated ethers are resistant to oxidation. So here's 3 common ones: isoflurane, sevoflurane, and desflurane. 3 different examples, just for your edification, but you wouldn't be tested on that. Now, another piece that comes in are heterocyclic ethers. So the oxygen can actually be in the ring system. We'll find out that nitrogen can also do this. So anybody who can form more than one bond, anybody who can form 2 heteroatom carbon bonds can actually insert into a ring system to make what we call a heterocyclic compound. So if oxygen is our atom that we're working with, then we can make a heterocyclic ether. And these turn out to be really important. They're not particularly reactive, and they're really good solvents. They're often used as solvents for organic reactions because they work to dissolve nonpolar compounds, but they're also, so they have a polar part and a nonpolar part. So they really work to be pretty universal solvents. And a couple of them that are very important for chemists that we use very often are THF, that is tetrahydrofuran, and 1,4-dioxane. And just as a side point, dioxane, you may have heard of something called dioxins. Dioxins are something very different. So if you want to discuss them in class, you can mention it, and I'll go over that with you in class. But dioxane and 1,4-dioxin are different compounds, and they're just standard ethers. It turns out that heterocyclic compounds are very important in a lot of medicinal chemistry. They're used very regularly, and here's an example of ethers that are used in cancer treatments. They inhibit cancerous cell growth and division. So next, let's go over the physical properties of ethers. And you guys, hopefully you could start to quickly deduce what we have, because ethers have a polar carbon-oxygen-carbon bond. So we're going to have dipole-dipole forces. So those are stronger than, of course, our hydrocarbons. So they're going to have elevated melting points and boiling points relative to hydrocarbons. And then you have a partially negative oxygen because of that dipole moment. So it has a lone pair of electrons, and it can accept hydrogen bonds from water. So it really is a hydrogen bonding system. And so the small ethers are soluble in water. As the hydrocarbon size gets bigger, the overall polarity starts to get damped substantially, and the solubility of the ethers in water goes down. Next up, and it turns out that ethers are not particularly reactive species. They're used as solvents. They do have some reactivity patterns, but we're not going to cover those. Next up, we have amines, and now we're going to switch to nitrogen. So amines are a class of organic compounds with nitrogen bonded to carbon. And it can, of course, nitrogen can form 3 different bonds, and so we can have 1, 2, or 3 carbons bonded to the nitrogen. And all of these are classified as amines. okay? So sometimes we'll call them an amino group or an amine group. And you can deduce what its shape is because the nitrogen, of course, has a lone pair on it. So it is going to be a trigonal pyramid shape because of the 4 electron groups with one being a lone pair. And it turns out amines are really important. They're all over the place. You find them in a lot of pharmaceuticals, and they're also in lots of biological systems. They're a main component of proteins, and they're present in both DNA and RNA, so they're important for genetics as well. Now, all the amines, it doesn't matter how many alkyl groups we have attached, we classify all of them as amines, but we do provide some differentiation. So we have primary amines, and a primary amine has one alkyl group attached to the nitrogen, and then the other 2 substituents, the other 2 bonded species to the nitrogen, are both hydrogens. So the general formula then is RNH2, where R is an alkyl moiety. A secondary amine has a nitrogen bonded to 2 different alkyl groups. So there's 2 nitrogen carbon bonds and then 1 hydrogen attached to a nitrogen. So the general formula is R2NH or RR'NH, depending on whether they're the same or different alkyl groups. Finally, tertiary amines have a nitrogen that's bonded to 3 carbon atoms, and they have the general formula R3N or R2 R'N or RR', depending on whether they're the same or different alkyl groups. So our approach to naming the amines follows similar to what we did with alcohols. For primary amines, we remove the final E of the parent alkane and replace it with amine. So down below here you'll see 3 different versions of this. The first one, figure A, we have an ethyl group attached to NH2, so we call that ethanamine. Then in B we have a N-propyl group, or 1 propyl group, so that's 1 propylamine. And then in the third one we have a propyl group attached to nitrogen, but we're bonded to the 2nd carbon, so we call that 2-propylamine. Sometimes we might even call that isopropylamine. Secondary and tertiary amines have more than 1 R group, so now we need to delineate this. What we do is we use the longest R group as the parent amine name. So for example, in figure A here, we've got a methyl group and an ethyl group. We use the ethyl group because that's the largest chain. So the NHCH2CH3, that represents our parent chain. We call that ethanamine. And then we add N, and then the alkyl group to indicate that the nitrogen has a 2nd alkyl group on it, in this case a methyl group. So we name the shorter R groups as substituents, with the N to indicate they're located on the nitrogen atom and not on the hydrocarbon chain. And so here's examples. In B we've got a propyl group and a methyl group. So the propyl group means that it's going to be a propanamine, and then the methyl group says that's an N-methyl, 1-propanamine. And if it's tertiary, then, as in C, then we have a propyl group. That's going to be propanamine. And if we've got 2 methyl groups, we could call that NN-dimethyl. And we put the 1-propanamine to indicate that the nitrogen is attached to the terminal carbon on the propyl group. And if the 2 alkyl groups are different on the nitrogen, as we have in variant D here, we would call that N-ethyl, N-methyl, 1-propanamine. There are common names for amines, and you'll see these very regularly. They take the alkyl name of the R group and add the suffix amine. So for a branched R group, the table we covered earlier are used. And the common names for secondary and tertiary amines list all the R groups in alphabetical order, followed by amine. So just as we see this, for the first example, in A here, the nitrogen is attached to the carbon. We call that an isopropyl, so we'll just call that isopropylamine. We could call that 2-propylamine, but isopropylamine is common. And then you can see in variant B here, methylpropylamine, that doesn't include the N. We should put the N on there to indicate it's N-methyl, but it's very commonly done. You'll see methylpropylamine. And then the third one, rather than having NN-dimethylamine, trimethylamine is the more common name. Now, nitrogen, of course, has a valency of 3. It can form 3 bonds. So this can stick into hydrocarbon rings and replace a CH2 unit. And so this is what is called a heterocyclic amine. A heterocyclic amine has the nitrogen atom within a hydrocarbon ring. And there's a variety of them that are very important. These are heterocyclic amines are ubiquitous in biochemistry and biological chemistry, and very important for drug molecules, DNA and RNA are derivatives of purine and pyrimidine, which are shown here as heterocyclic amines. And there are amino acids that are derivatives of these as well. So let's take a quick look here. These are just ones that you should recognize. We've got pyrrolidine and piperidine. These are the unsaturated 5- and 6-membered ring systems. Pyrrole and imidazole are the 5-membered unsaturated systems with 1 and 2 nitrogens respectively. And then pyridine, which is a hugely important compound. Pyridine is you see this all over the place. Pyridine is benzene with one of the CH units replaced by a nitrogen atom. So notice that the nitrogen atom in pyridine has no hydrogens on it because it has 3 bonds around it. But it does have a lone pair, which confers a unique set of reactivities. Pyridine and benzene are 2 common solvents, but they're very different in their chemical reactivities. And some other important bases, pyrimidine and purine, are shown here. Now, the physical properties of amines kind of follow what you'd expect. Primary and secondary amines are hydrogen bond donors and hydrogen bond acceptors because they have a nitrogen-hydrogen bond. And so they have hydrogen bonding as their dominant molecular force. That means that's going to confer water solubility, and it's also going to increase the boiling points and the melting points relative to the corresponding hydrocarbon. Now, the primary amine has 2 nitrogen and hydrogen bonds. It can make more hydrogen bonds, and therefore it tends to have even further higher water solubility and boiling and melting points. Now, tertiary amines lack that nitrogen and hydrogen bond, so they're simply driven by dipole-dipole forces. So the boiling point of primary amines are the highest, secondary amines are next, and then tertiary amines are the lowest for a given size, molar mass. And from the solubility, tertiary amines are not hydrogen bond donors, but they are hydrogen bond acceptors, so they're soluble in water. All amines that are relatively small hydrocarbons, whether they're primary, secondary, or tertiary, are all soluble in water. But as the hydrocarbon group increases in size, the water solubility decreases. For chemical reactivities, the most important thing we're going to think about is acid-base chemistry. And to understand this, let's go back to basic chemistry and let's think about a base we learned about very early on, and that is ammonia, NH3. Ammonia reacts with water to form ammonium and hydroxide. So it releases OH minus. Ammonia is a base. It's a weak base. And if you replace one of those hydrogens with an alkyl group, you have a base. In fact, you can replace a couple of them, 2 or 3 of them. You can replace all 3, and they'll still be basic. So after an amine reacts with water, it produces a alkyl ammonium species. So if it's like, take as an example, methylamine and reacts with water. Methylamine goes into water, it forms the methylammonium ion and hydroxide. Now, it's not as strong a base as ammonia is. Ammonia is a weak base, so methylamine is an even weaker base, but it's still basic. And you could do the same thing with dimethylamine or trimethylamine. So when the amine reacts and produces the alkyl ammonium species, you have a conjugate acid base pair, and they only differ by a hydrogen atom. So the alkyl ammonium structure looks as shown in figure A. This is actually a tetrahedral structure. We put a positive charge on the nitrogen because it turns out that if we do a formal charge count, it turns out the nitrogen is slightly positive. So if you want to basically handle this and make a pure material out of it, you have to add a negative charge. And so if you add a halide as an example to give the negative charge, you can make what we call an alkyl ammonium salt. So alkyl ammonium salts are solid versions of the amines as their acid salt. So an alkyl ammonium ion is a weak acid, just as an ammonium ion is a weak base. Now, alkyl ammonium salts tend to have higher water solubilities than the corresponding amines because they're ions, and ions dissolve in water very readily. That's the ion dipole bond, which is the strongest intermolecular force that we have. And an example of this is epinephrine. Sometimes it's called adrenaline and used to treat anaphylaxis. If you're going into anaphylactic shock or having an allergic reaction or having cardiac arrest. And so the drug is formed as the alkyl ammonium salt, which dissolves more readily in blood and causes it to be more effective than just the amine itself. Now we have to talk about one more variant of amines, and that is what's called quaternary ammonium salts. And this will seem a little unusual, so I have to take a moment to think about this. But these are very common and very important. Because we think, okay, nitrogen has 3 bonds and a lone pair. What if we do some chemistry to get rid of the lone pair and put a covalent bond there instead? And there are ways for us to do this chemically. That forms a nitrogen with 4 covalent bonds. It doesn't have a lone pair, and since it's sharing all of its electrons, this causes it to have a formally positive charge. So then if we want to make the pure version of this material, not just dissolved in water, we have to add a negative charge with it. And so this is called the anion, X minus, and that could be probably most commonly chloride. And so this is what we call a quaternary ammonium salt. These are not acidic species. All four of the bonds to nitrogen are nitrogen-carbon bonds. So these are stable systems that are soluble in water. They have a high water solubility. So choline is an important kind of an example of this. And choline phospholipids are also components of cell membranes. Now let's move on to aromatic systems. Imagine we take benzene and we take off one of the hydrogen atoms and replace it with an OH. We can do that very easily, and that's a compound called phenol. So just like we had benzenes or aromatics, we can have phenols. And phenols are also aromatic compounds because they have that 6 double bond electrons floating around a 6-membered ring, so it's our 4n plus 2 electron rule. Phenol is aromatic, but it's got an OH group on it. And just as an aside, it turns out the OH on phenol is acidic. So phenol's a corrosive material. Actually acts like a little bit of an acid. So you can also do the same thing with an NH2 group. So you can take a hydrogen atom off of benzene and replace it with NH2, and that forms a compound called aniline. Aniline is a base, and it can pick up a proton from water to form anilinium, we call that. But aniline is also aromatic, just like phenol is, just like benzene is. And in this case, if we look, we can look at it from the perspective of benzene, or we could look at it from the perspective of the functional group. So from the perspective of the functional group, the aromatic hydrocarbon is attached, and that's the R group, and we call that an aryl group. And so rather than putting an R there, we'll often put an AR-OH. So phenol then would be AROH, aniline would be ARNH2. Now the names, of course, we've already kind of given this. We've got phenol and aniline, but then we can do substitutions on there. We can put other functional groups onto the benzene ring, and then have to rename that. Now, if we do this with phenol, of course, the hydroxyl group on phenol defines the carbon attached to oxygen as position number 1. That's carbon 1. So then anybody who's attached to it, any other substituents on there, will be numbered correspondingly. Or we could also use the ortho, meta, and para nomenclature we had from last chapter. Here are some important phenol-containing organic compounds. One of them is tyrosine. This is an amino acid, very important amino acid. You find it in meats, nuts, seeds, fruits, and your body uses this for a lot of different important applications. Tyrosine is an important nutrient for us. And another one that's important is capsaicin. You probably know this that gives the heat to hot peppers and hot foods. So it's as it says here, it's a deterrent to some herbivores, but obviously people eat it in some cases if you like hot food. Now, anilines are a little more complex than phenols because the nitrogen can have other alkyl groups attached to it. So again, the carbon atom bonded to the amino group is still carbon 1. That's the starting position. And then anything bound to the aromatic ring will number correspondingly relative to the nitrogen. So for example, in structure B here in our figure, we have 4-methyl-aniline because you can count around 1, 2, 3, 4. The methyl group is attached to the 4 position on the benzene ring. Or we could also call that paramethyl-aniline. And in C, we've got a situation where we've got chlorine on the 2 position, 2-chloroaniline, or orthochloroaniline. But then if the substituent is on the nitrogen, then we use our N nomenclature. So R group attached to the N atom of the amino group is delineated with a prefix N to identify its location. So in structure A here, we have aniline, but then we have a methyl group attached to the nitrogen. That's called N-methyl-aniline. So you can look at A and B. A and B are actually isomers of one another. They're structural isomers, right? The methyl group and the hydrogen are just swapped back and forth from the nitrogen position to the ring position. They have the exact formula mass, the exact same molar masses, the exact same chemical formulas, but they're structurally and chemically very different. Both the phenols and the anilines have nonpolar aromatic rings, and those are obviously very important. But they've got a polar functional group that can undergo dipole-dipole interactions and hydrogen bonding, right? That's a big key. So phenol and aniline are solids at room temperature. That contrasts with benzene, which is a liquid. And they're actually soluble in water due to the hydrogen bonding between the OH or the amine functional group and water. So here's a summary of alcohols, thiols, ethers, and amines. We've kind of gone through this whole group here. And our naming approach, our general structure. And so starting off with alcohols, we've got ROH. We name that the alkane name plus OL, so like ethanol is an example. The second group are phenols, which have an aryl group attached to OH. So then we call that alkyl plus the phenol. So like, for example, 4-methylphenol. Then we had thiols, which had R bound to an SH. So we just name that using alkane plus thiol, ethane thiol. We have the ethers, where we've got two different alkyl groups attached to the oxygen atom. And the proper naming is we take one of the alkyl groups and make, like, for example, methoxy and then ethane, or we might call that ethyl methyl ether. Then we have amines, which have R bound to NH2, and we have the alkane plus amine naming system. And remembering, if we have multiple substituents, using the N, capital N nomenclature. And then finally aniline, the aryl group bound to NH2, and we can name that depending on whether the alkyl group is attached to the ring system or to the nitrogen. Now, what happens when you have multiple functional groups? Well, it turns out that if you have multiple functional groups, one functional group is given priority, and of the groups we've looked at so far, alcohols, it turns out have the top priority over halogens, thiols, ethers, and amines. But we're not going to go into complex naming structures right now. We want to make sure that we get all the basic naming down and get very proficient with that. So thinking about substituents, functional groups as substituents, here are a series of examples of what this looks like. So the halogen substituent, that's just a halide attached onto some structure. And of course, here, of course, we're treating the alcohol as the primary priority system. So if we go to name a halogenated alcohol, then we would call it, for example, here, this is 3-chloro-1-butanol. If we had a thiol attached to an alcohol, we might call that 2-mercaptoethanol. If we have an ether, we might call that 2-methoxy-1-propanol. And then an amine, we might call this 2-amino-1-butanol. So these are examples of that priority system. So let's kind of do a quick comparison of overall physical properties for our various systems for alcohols, ethers, and amines. So ethers can be hydrogen bond donors. They can't form hydrogen bonds with other ether molecules, so they tend to have an overall weaker intermolecular force in their pure state. So alcohols are kind of the strongest hydrogen bond systems. Amines are they're next up. They're not quite as strong hydrogen bonders. Ethers are dipole-dipole forces. And so if we're comparing these, we can kind of see how they behave. So alcohols exhibit the strongest intermolecular forces, larger than amines, because of the difference in electronegativity. That completes our discussion on Chapter 13.